So good morning to students, and today I am going to talk about the power transmission in pipe. So if you like my lectures, so please subscribe and you can share this lecture with your friends. So if you want to go to my previous lecture, you just click on the I button above the video, so you can go to my previous lecture. So now I am going to start with a new topic that is called the power transmission in pipe. So the power transmission in pipe, I can write down. So the power transmission in pipe, it depends on two factors. So first one is called discharge, the flow rate in the pipe. So you can write down the discharge. So the discharge in pipe, and second factor, it depends upon the total head available at the inlet of the pipe. So I can write down the total head of water or liquid. So the total head of water which is available at the inlet of the pipe. So suppose this is my pipeline. So suppose this is my reservoir. A reservoir in which I connected one pipe. So this is I connected one pipe. So suppose this is the free surface of my reservoir, and this is the head which is available head, and this head is converted into the kinetic energy. This is the potential energy which is available in the reservoir. That potential energy now is converted into the kinetic. Suppose this is this point I am choosing the inlet point 1, and this point is called my outlet point 2. Here the water is flowing with a velocity of v, and this is my length of the pipe L. So I can the power available at the inlet zone of the pipe. So I can, what is the power formula? Power will be equal to m dot, this is G into H. What is this m dot? M dot is the flow rate. What is the flow rate? Again, this is rho into Q. So what is the flow rate in the pipe? So the power formula to calculate the power in a pipe flow. What is the power available at the inlet zone? If you can find out, that is rho Q into G into H. So this is the formula by which you can calculate the power. Okay. Now what is this H? Let me clear about this notation. What is H? So H is the head of water available at inlet of pipe. So this point is called inlet. So for this point is called inlet point. So I can write down H will be equal to head available at inlet zone of pipe. What is the head available at inlet zone of the pipe? What is this L? L is called the length of the pipe. Okay, L is length of pipe. What is this D? So this D is called as, this is diameter of the pipe. So this is called diameter of pipe. And B is called, let me write down here. I'm writing. So here writing this. B is called, this is velocity of flow of water in the pipe. What is F? F is called friction factor of the pipe material. This is called friction factor. Okay. Now I am going to derive what is the power available, or what is the power available at the exit point. Okay, what is the power available at the exit? So all this note you can get this PDF note from the description part of my video. So go to the description part, you click the link and download this PDF. So now if you want to find out, so this is the pipe, this is the reservoir. Okay, so this is my reservoir, and this is the free surface. This is the head of the water in the reservoir. This is the head of the water is in the reservoir, and this point is the inlet point. Suppose this point is my exit point where the water is flowing with the velocity v, and this is the length of the pipe. So if I want to write down the power at inlet point, so I have to write down that the power available, better write down the power available at inlet point. What is the inlet point? This is E1. 1 is the inlet. So what is the power available this inlet point? That is m dot g is. Okay. So what is m dot? This is rho q into g into h. This is the my power available at the inlet. So what is the power available at the outlet point? So before we find out what is the net head available at outlet point, we have to find out what is the net head. So net head available at outlet point. So outlet point. What is the net head available at outlet point? What is the net head available? So you can write down H net. That is the total head available at the inlet point minus the head loss due to friction. Okay, minus the head loss due to friction. So this is the net head available. So if you want to find out the power available, so if you want to, this is power available at this outlet point. What is the power available outlet point? You want to write down this is P2. Okay, this point number 2. That is m dot g into h minus this head loss due to friction. So you can write down m dot is rho into q, g into this is h minus head loss due to friction. So this is my outlet power. So what is the head loss due to friction? Head loss due to friction we already know. This is F L V square divided by 2 into g into this pipe diameter. What is this capital D? This is called pipe diameter. Okay, this pipe diameter. If you want to find out what is the efficiency means I can write down this is output power divided by this is input power. What is output power? This is P2 by this one is P1. What is P2? If you want to, this is rho QG H minus this HF divided by this is rho QG into H. So I can simplify this one. This is H minus this is HF divided by this. So this is my efficiency. Okay, this is my efficiency of the power transmission. Now we want to find out what is the condition so that we can get the maximum power at the outlet point. What is the condition so that we can get the maximum power at this point number 2, at this job. So this point number 2, what is the condition? So now I am talking about the condition. So we know that for this maximum power transmission, the power is transmitted from the point number 1 to point number 2. So for maximum power transmission, so we can write down one condition. Okay. So first of all, what is the power available at point 2? The power available at point 2 will be this is m dot g into this is h minus head loss due to friction. So this will be equal to rho q into g minus h. What is the head loss due to friction? This is F L V square divided by this is 2g into d. Then HF will be equal to this is F L V square divided by this is 2g into d. So this is my head loss due to friction. Okay. So now we know that this discharge will be equal to continuity equation area into velocity. So in the case of the discharge, I can write down P2 will be equal to rho, this is area into velocity into g into this h minus this is FL v square by this is 2g into d. Now I can write down this power available at outlet point will be equal to rho A into Z. So I can take this B inside this bracket HB minus this is FL VQ divided by this is 2G into D. This is my condition. Okay, now you see the density of the fluid is constant. If the cross-sectional area of the pipe is constant and G acceleration into gravity is also constant, and the head available is also constant. So if all parameters are constant, this power is a function of velocity. Okay, so if power is a function of velocity, means there is only one variable that power is depend upon the velocity. When the velocity will be maximum, we can say the power will be maximum, or like that the velocity will be less, power will be less. So we can derive one condition that for maximum power, okay, so for maximum power at outlet, for maximum power at outlet point number 2. So this from maxima and minima principle, dP by dV will be equal to 0. So dP by dV will be equal to 0. So now if you solve this equation, so now I'm solve this. This is I can write down dP2 by dV will be equal to 0. So this is d by dV of what is P2? P2 this is rho Ag into this is H minus this is H into V minus this is FL VQ divided by this one is 2G into T will be equal to 6. So now I can derive one condition. Suppose this rho Ag are constant, I can take out for rho Ag and this is coming out to be H minus this is 3FL V square divided by this is 2G into T will be equal to 0. So this rho Ag is constant, it cannot become 0. Okay, this rho is constant, this cannot become 0. So only this can be possible 0. So this H minus 3FL V square divided by this is 2GD will be equal to 0. So what is this one? HF, we know that this is FL V square by this one is 2G into T. So I can put here this is H minus 3 times of HF will be equal to 0. Or I can say for maximum power transmission, the HF will be equal to H by T. So this is the condition when we can get maximum power at the outlet. So I can write down, hence it means that power transmitted, so power transmitted through pipe is maximum, so is maximum when head loss due to friction in pipe H is equal to one third of the total head. This is a very popular objective question. So it can ask you what is the condition that the power at the outlet point of a pipe will be maximum. So you can directly say this one is when this will be satisfied, the head loss due to friction, when the one third of the total head available at the inlet point, then we can get the power at outlet point is maximum. So what is the efficiency? If you want to find out, so what is the efficiency? So maximum efficiency. So maximum efficiency will be equal to power outlet minus power inlet. So let we know that this is H minus HF divided by this is H. So this is H minus this is H by 3 divided by H. So this is 2 by 3. Or in percentage we can get this is 66.67%. So this is the maximum efficiency we can get at the outlet. 66.67%. Okay. Now I will solve one numerical for you. So what is saying? It is saying, it is first numerical. So a reservoir is there. Okay. So a reservoir is there, and this is connected to one pipe. And length of this pipe is given to you. This length is 5, and the head at this inlet point. This is the head at inlet point. This is H. Okay. And this is going with a velocity v. Okay. So now it is saying the length will be equal to this given to you with 2500 meter. And the power transmitted also is given to you. The power transmitted. What is the power transmitted given to you? That is 120 kilowatt is given to you. And it is saying pressure at inlet is given to you. The pressure at inlet. So pressure at inlet means this pressure at point 1. Suppose this is my amplitude, this is my 1 point. And suppose this point is amplitude, this is 2 point. So pressure at inlet is given to, that is 4000 kilonewton per this is meter square is given to. So it is asking what is the head loss due to friction. So first of all asking it is head loss due to friction, we can find out. So head loss due to friction we can find out. Second is asking what is the diameter of the pipe. What is the diameter of the pipe? Okay, it is asking for capital D. In second case it is asking what is the power at outlet. Okay, so power at inlet is given to you. So now it is asking point what is the power at outlet. Okay, this is two things asking. So now pressure at inlet means it is given to you. So this P1 pressure at inlet is given to you. This is 4000 kilonewton per this is meter square is given. So I can find out what is the available head at inlet, that is P1 by this is I can do rho into G. So this is 4000 into this is 4000 into this is 10 to the 30 Newton per meter square. The density of other 1000 into this is 9.1. So what is the head available at the inlet? This is 407 point this is 7 meter. So this is the head available at the inlet. And here also it is given pressure drop. It is given the pressure drop in between point 1 and point 2. What is the pressure drop? It's given. This is 800 kilonewton per meter square. This is the pressure drop. Okay. Pressure drop is why? That because of the head loss due to friction. Okay. So if you want to apply the Bernoulli equation in between the point number 1 and point number 2, so you will get the P1 by rho G, okay, minus this P2 by rho G will be equal, that is nothing but equal to head loss due to friction. Okay, so head loss due to friction. So now this I am writing this point as, so P1 by rho G, it is given you as this head loss due to friction. I can find out the pressure drop is given to you as 800 kilonewton per meter square. 800 into this is 10 to the power 3, and this is why it is coming out to the density of the water into this is 9.8. So head loss due to this friction is coming out to be 81.5 meter. Okay, 81.5 meter. Now, if you ask, if student is not getting how this value P1 by rho G and this P1 by rho G and this is how it is coming. So, if you connect one manometer right over here, if you connect one manometer right over here, so suppose what will happen? There will be some pressure drop. Okay, the deflection of the manometer is coming out right over here. Okay. So now if you want to write down the equation in between this point number 1 and point 2, so this is P1 by rho G plus this is A1 square by 2G plus this is Z1. If you apply the Bernoulli equation in point number 1, how the equation is came, I just make you understand. P2 by rho G plus this is V2 square by 2G plus Z. Here Z1 and Z2 are same because this is a horizontal axis. Z1 and Z2 are same. And see at point number 1 and point number 2, the cross-sectional area is uniform. So V1 also will be equal to V2. So this kinetic head also neglected. So there is a loss of energy. So I can write down here this is plus the head loss due to friction. So if you take this equation P1 by rho G minus this is P2 by rho G, that is what will be equal to head loss due to friction. That's why I am written right over here. Okay. So now head loss due to friction is coming out to be this one. Now you have to find out what is the diameter of the pipe. So first I am writing here the diameter of the pipe. So this is diameter of pipe. So what is the diameter of this pipe? So this is my reservoir. Here is the head available is H. This is my length of the pipe, and this is my diameter of the pipe. We have to find out. So what is the available head at inlet? The available head at inlet. So the available head at inlet, suppose this point is inlet point. So this is 1 and this is the exit point. So this point is ending 2. So available head at inlet H1 I can write down. So that is will be equal to, already found out this 407.7 meter. Okay. So net head available at outlet. What is the net head available at outlet point? Outlet point. What is the net head available at outlet point? That is, if you enter this head as point number 2, because that is H1 head level weight minus some head loss due to friction. So what is this is 407.7 minus head loss due to friction. We found out this is 81.5. So that is coming out to be 326.2 meter. So now this is the head available at point 2. Okay. Now we want to find out what is the power at outlet. Okay. So I am writing here. So this is power at outlet. Okay, this power at outlet we have to. Okay, power at outlet. So here actually I told you. So this point here. Okay. So here power transmitted is given to you. So this is power. So this is P2 is not asking. So this is 120 kilowatt. It is given to you. Power transmitted. So it is asking what is the discharge in the pipe. Okay, it is asking you have to find out what the discharge in pipe. So if you want to find out the discharge, so the power at outlet, so already the power transmitted is given to you, that is 120 kilowatt. That is given to you. So you have to find out what is the discharge. The second point is asking what is the discharge in the pipe. So we know this power at outlet will be equal to m dot G into this is H minus this is HA. Okay. So now if you put this one, P2 is how much? This is 120 and this is we have to do what into there 3. M dot is what? Rho into Q into G into H minus HF we already found it. This is nothing but equal to power head available at point number 2. So now if you solve this equation, now I am solving this equation, that is 120 into this is 10 to the power 3 will be equal to, that is rho Q G into H minus this is head loss due to friction. So this is 120 into this is 10 to the power 3. Density of the water is how much? 1000 kg per meter cube, and Q we have to find out, and this is 9.81, and this H minus HF we already found, this is 326.2. So if you solve this equation, the discharge is coming out to be 0.0375 meter cube per second. So this is the discharge in the pipe. Okay. So discharge we found out. Okay. So discharge we found out. So now I have to find out what the diameter of the pipe. So we know that this discharge will be equal to, so this discharge we can write down. So the discharge will be equal to area into velocity of flow in terms of the continuity equation. So what is discharge? This is 0.0375 will be equal to, this is pi by 4 into this is d square into the velocity. So what is this velocity of flow? Velocity of flow will be equal to, this is 0.0375 into this is 4 divided by this is coming out to be pi d square. So this is the velocity of flow. Now we know that head loss due to friction will be equal to, this is FL d square divided by this is 2g into t. So what is this head loss due to friction is given? That is 81.5 meter is given to us. So now F is given to you, this is friction coefficient of friction is, so we multiply 4 into 0.006 into this length. Length is given to 20.5 kilometers, so you can write in meter, into this B. B you can write down right over this one. So B you can write down this one. So this is 0.0375 into 4 divided by this is pi d square to the power whole square. Okay. So this is 2 into this is 9.81 and this is d. Okay. So now if you solve this equation, so the diameter of pipe is coming out to 0.15. This is 35 meter. Or this is 153.5 millimeter. So this is the diameter of the pipe. Okay. So this is the numerical based upon this one. Now suppose you want to find out what is the efficiency. Suppose now you have to find out what is the efficiency. So efficiency we can find out the outlet power by inlet power. So this is nothing about H minus this HF divided by this H. So what is this one? This is 407.7 minus this is 81.5 divided by this one is 407.7. Okay. So we can find out the efficiency from here also. What is the efficiency of the system? So this is the numerical of this based upon the power transmission of the pipe. So now I am going to talk about the power available from nozzle. So available. So this is power available from nozzle. What is the nozzle? So nozzle is what? Nozzle is a tapering mouthpiece which is connected at the outlet of the pipe to convert all the energy into the kinetic energy. Okay, so the aim of the nozzle is to convert the pressure energy, all this potential energy, kinetic energy, every energy into this kinetic energy. So the water which is coming out of this nozzle with a very high velocity. What is the application of the nozzle? We can use this nozzle in the power development, power generation. In power generation, what is there is a penstock is there, and at the outlet of the penstock, a nozzle is connected. So the water which is coming out of the penstock with a very high velocity, and when the water will strike with these blades of the turbine, then the turbine will start rotating. So there is application of this nozzle, and there is application in firefighting also. Okay, in firefighting also we can use this nozzle principle, and there is also the application is mining also. So we should choose the diameter in such a way that so that we can get the power at outlet will be maximum. Okay, that is how we cannot arbitrarily choose the diameter of the nozzle. We can choose diameter of the nozzle is a basic way. So there is some logic. Okay, so now I am talking about, suppose this is my reservoir. So suppose this is my reservoir and this is my pipe. This is my pipe, and this outlet point a nozzle is connected. So the nozzle is connected. Okay, so this is my head available at the inlet. So this is my head available at the inlet, and this is my length of the pipe. So this is my length of the pipe. The water is coming out from this. Suppose this is velocity small b. The diameter is suppose this is small d, and the cross-sectional area of the nozzle is small a. And there is this pipe diameter is this is capital D. And this area of the pipe is capital A. Now suppose I am choosing 2 points. Suppose this is point number 1, and suppose this is I am choosing the point number 2. Okay. Now if you apply, now I am applying Bernoulli equation. Bernoulli's equation in between point number 1 and point number 2. So write down the equation P1 by rho G plus this is Z1. Okay. So P1 by rho G plus Z1 plus this will be your P1 square by 2G will be equal to this is P2 by rho G plus this is Z2 plus this is P2 square by 2G plus head loss due to friction. So here P atmospheric pressure is acting at both the parts. So you can write this is P ATM by this one is rho G plus this Z1 is how much? This is suppose I am choosing this part. So on this part I am choosing this one my datum line. So this is I am choosing this one is my datum. So what is that this? This is my Z2. Z2 will be equal to H. Oh, no, so Z1 will be equal to H. Now here this Z2 value will be equal to 0. Z2 will be equal to 0. So this will be H plus V1 square by 2G. The velocity at reservoir is very less because Bernoulli equation is only applicable for steady flow. The variation we cannot see naked eye. That is our objective. So again 0 square by this one will be 2G. Will be again this is P atmospheric divided by this one is rho G plus this is Z2 with 0, and there is a velocity in V small v square by 2G, and this is FL exam this is V square capital V square by 2G into T. So now this is our cancel PATM form. So the head which is available at inlet will be equal to small v square by 2G plus this is FL v square divided by this is 2 into 3 into D. So this is equation number 1. Okay. Now if you apply the continuity equation. So now if you apply the continuity equation. So continuity equation I am writing. So the discharge will be equal to capital area of the pipe into velocity flow in the pipe will be equal to area of the nozzle into the small v. Okay. So from here if you write down a V will be equal to this is small a into small v by this is capital A. So now this is my equation 2. Now if you solve equation 1 and equation 2, so if you put this velocity will be right over in equation 1, then we'll get the nozzle velocity will be equal to this is square root of this is 2GH divided by this is 1 plus FL this is A square divided by this is D into A square. So this is the velocity. So this is the velocity of flow in nozzle. Okay, this is the velocity of flow in nozzle. Now we know that what is the head available at inlet, that is small v square by 2G plus the head loss due to friction. So we know that this H minus this HF will be equal to small v square by this is 2G. So this is 2. Okay. So now what is the efficiency? Efficiency will be equal to power at outlet point by power at inlet. Okay. Inlet point. So if you draw this one, so this is my reservoir and this is my pipe. Okay, this is my pipe. And this is my nozzle. This is my nozzle. Where is coming out with the velocity small v. And so this is my inlet point. And this point is my outlet point. So I can write this is power at outlet. Power at outlet by power at inlet. So output power by input power. So this is nothing but we can already find out this is H minus HF by this one is H. Okay. Now this efficiency I can write down. What is this H minus HF? So we know this is V square by the small v square by this is 2G into H. Okay, this is u square by 2g into this is h. And if you also want to find out what is the condition so that we can get maximum power at the outlet, then that same thing will go. The head loss due to friction will be equal to h by 3. This is also the condition in nozzle case when we get the power at outlet point will be maximum. Okay, so this is the equation of the efficiency. Okay, this is the efficiency we can find out. So now if you use the formula, so we already found out the velocity of flow will be equal to what? This is 2g into h divided by this is 1 plus fl small a square divided by this is d into s square. This is the velocity. Now if you solve this equation, you put this velocity right over here, the efficiency will get, so efficiency will be equal to 1 by f, this is L into s square divided by this is d into s square. So this is the formula by which you can calculate efficiency in nozzle. So efficiency in nozzle you can calculate. And we know that for maximum power transmission, so for maximum power transmission, so maximum power transmission, the head loss due to friction will be equal to h by 3. So head loss due to friction will be equal to h by 3. So what is the maximum efficiency? The maximum efficiency will be equal to h minus this is hf divided by this h. So this is h minus this is h by 3 divided by this h. So this is coming out to 66.67%. Okay, 66.67%. Now you want to find out what is the diameter of the nozzle so that we can get maximum power at the outlet. What is the condition? We have to find out. So now to find out the efficiency we got, this will be equal to 1. So efficiency will be equal to, so this is will be equal to 1 divided by, this is 1 plus FL S square divided by this is D into S square. Okay. Now for this one to be maximum, what is this efficiency? This must be 2 by 3, or we can write down 67%. I am writing 2 by 3. So this will be equal to what is 1 by 1 plus FL S square divided by this will be equal to D into S square. Okay. And this is for maximum power efficiency. Maximum efficiency is the condition. Now we can solve this equation. This is, you can write down, this is FL S square divided by this is D into S square will be equal to how much? This is will be equal to 1 by 2. Okay. So now this is small a divided by this capital A will be equal to root over of D by this one is 2 into F into L. Now this what is? This will be equal to small d square by this is pi by 4 is common. This square will be equal to root over of this is D by 2F into L. Now if you solve again this one, so this is coming out to be, if you square both sides, this is D4 by this is D4 will be equal to D by this will be 2FL. So what is this D4? D4 will be equal to D to the power 5 divided by this is 2F into L. So now what is the diameter of this nozzle? This will be equal to D to the power 5 divided by 2 times F into L to the power 1 by 4. So this is the condition, the diameter of the nozzle. This is the diameter of the nozzle so that we can get maximum efficiency or maximum power at the outlet point. Okay. So this is the condition. This is the diameter of the nozzle for maximum power at the outlet. What is this F? So this F will be equal to this friction factor. So this F will be equal to this is friction factor. What is this L? This L is length of the pipe. So this is length of the pipe. What is this capital D? Capital is the diameter of the pipe. Diameter of the pipe. Okay. So this is the condition of to find out the diameter of the nozzle. Okay. So thank you for today's lecture. So in coming lecture, we will solve some numerical based on the this topic. This is power transmission. Again, we will solve some modules and this pipe. So in this lecture PDF you want to find out, you can download this PDF from the description part. There is a link is there. You click that link, you can get this PDF. And if you like my video, please share, subscribe and like the button. So thank you.